All right, okay, so the previous slide said how to make the compiler suite, and I had a bit trouble coming up with a good title for this as well. So it's basically doing stuff in compile time, which is just general meta programming basically. So as a quick intro, who I am. I started programming as a kid a long time ago. I've started with C++ also quite a long time ago. I haven't worked continuously with C++ since, but I have sort of kept it up to date at intervals. Studied at LTH, and I worked as a consultant since, and mostly fairly broad, but mostly doing embedded stuff. So I've been at Ericsson, Schneider Electric, and those kind of places. So embedded systems in general. I got the impression that a lot of you other guys here are from like the gaming industry and so on. So embedded systems, that's basically smaller computers. You typically have limited memory, and you typically have not so much CPU power. And if you have some program that's supposed to be run continuously for months or years, then it's also quite important that they are correct and don't crash or leak memory and so on. And yes, my impression, I'm not sure, I haven't done any statistics on this, but my impression is that it's mostly C, basically, in the better world. And there is some C++. It's a little bit conservative attitude towards C++, and if C++ is used in a better world, it's often kind of this sort of C with classes, where you sort of, okay, you can use certain features of C++, but no templates and no exceptions and stuff like that. In any case, so the talk is basically about doing stuff in compile time, and it's really just me going through a few examples of a few things I've sort of came up with in different projects, which I thought were cool, basically. And the process of coming up with nothing of this is like terribly original or whatever. It's just stuff. But the process of general coming up with sort of this compile time stuff is when you have some particular problem and you would like, and you have this, okay, it would be really nice if it's possible to do it like this. And you start investigating, could it be done? And then often you can actually, even if it's something that's sort of, when you start out and it's kind of outlandish, typically in the end you can sort of make it work, at least, sort of. So that's a general process of coming up with stuff, I think. And so this is I'm just gonna go through, I think, 3 examples of a few things. And as I said, there's nothing particularly original about this stuff. Like pretty much any idea you have, if you Google it online, you will find someone else who's done that exactly thing or something very similar to it. And the idea is not so much that you should just run home and take. I've put the code up on GitLab for you later as well, but the idea is not that you're supposed to run home and just take that code and use it, but more as a general inspiration for stuff to do. So it's kind of like a fashion show. So you're not supposed to actually go and dress like that. You're supposed to like take, this is the theme for the spring or whatever, I don't know. So, okay, so without any more stuff, let's just jump into the first example. So CRC42, which you may or may not know, it's cyclic redundancy check. So that's basically a checksum that you if you have some particular data, you can calculate this checksum over it, and if you send it to someone else, I have a slide there. If you send it to someone else, they can take the data, they compute the checksum using the same algorithm, and check is the checksum the same as was sent. Then if it is, or if it's not the same, then it's obviously an error somewhere, and if it is, it's a relatively high probability that is correct. And CRC you can do, there are like a billion different checksum algorithms, and you can design them in all kinds of ways. CRC for CRC in general, it's kind of useful, I guess, more low-level stuff, because it's one of the primary things is that it's robust about burst errors. So which is like this typical electrical errors where you have lots of bits errors in a row, basically. So it works quite well against that. So it's used for Ethernet and for zip file format and for gzip and for all these kinds of things. So that's the basic idea. Just have some chunk of data, you just calculate a checksum over it, and then you check in the end if on the receiving end if the checksum checks out, basically. And we're gonna skip over. In general, I'm gonna skip over quite a lot of details. And if there is anything that feels not like a detail I'm skipping over, then please just raise your hand. But okay, so the algorithm is specified by a polynomial, this long thing there, for instance. But we basically don't really need to care about it so much. The algorithm itself is pretty simple. So we can just, if you have a standard that specifies that you're supposed to be using a particular polynomial, you can just treat that as a magic number, more or less, when you implement the stuff. So, but this is a sort of a configuration thing that, depending on the standard, you might want to change this, basically. All right. So, say you want to build a CRC, a calculator for this CRC32 checksum. So, the API for something like this is very simple. You just make a class. You have a constructor, which you will typically want to throw in the polynomial. Maybe have a default value for it, depending on. I think the Ethernet standard is like the most common one. Then you have a method where you just add some chunk of data to it. Typically, you will want to do that iteratively. You won't necessarily have all the data available at once, but so you will typically instantiate your calculator, add a bunch of data iteratively, and then in the end you just want a method to sort of retrieve the result. And the result is just 4 bytes sort of condensed version of the data. Okay, so if you do a quick, sorry, this is just a sort of main thingy. So it's just to show how you use it. So you instantiate it, you loop through the data in a file, add it to the calculator, and then in the end you just print out the result, basically. So, and here's the first version. It's pretty straightforward. You don't need to necessarily go into you don't need to go blind on exactly what the code does, but basically this is just a function. It takes a value as input and it throws a value back as output, or return value. And above you have the constructor. You just add, so you just loop through each byte of the chunk of data, and you just you will call the calc CRC value for each byte of the input data. So that's pretty much it. And this is the state where it just keeps the current value, whatever it has. So this is the first version. We're going to go through this a little bit, sort of like an evolution of things. But obviously, this is kind of wasteful to do, because you're calling this function even if you inline it, and when you're calling this for each byte of the data, so it's kind of not that fast, basically. And if you look here, you're ending it by FF. So the only possible input values here is 0 to 255, and it only depends on this polynomial and the input value. So it's you call calc CRC for each byte. It's a pure function because it only depends on input. That has no care about state. There's only 256 possible inputs, as I said, and so obvious thing to do is to make a pre-computation table. So you don't need to, when you're adding data, which could be like gigabytes maybe, you don't need to call that function for each byte. You can just run through all the 256 values once, and then you can just look it up in a table. So here's with a table. So instead of calling the function, you just look it up we just look up the value in the table, which we have down here below. And this is the class for the table. So just when you instantiate, you just loop through it and just basically call the same function, and you store it in an std array. So that's pretty straightforward. A few things to note. Yeah, you're using table lookup instead of a function call. You're storing 4 times 256 bytes, so that's 1K memory. But also when you need the code for actually generating the table, so this isn't a lot of memory, but it is memory that it's using. This is semi-true. You could definitely instantiate it with different polynomials. But it's marginally less flexible than the previous version. But you could make it less. You could make it more flexible. Okay, so say that we don't want to go through the work of generating table in runtime, and we also, the code for generating the table in this particular case it's not very much, but it is data as well. And if you have a small system, you might not want that. So third version is basically the same as before, but now we're using static data instead. So we just have this. So this is identical to the previous version, and our CRC42 table instead is this. So basically just print out the stuff from the previous version and just have it as static data. So with this is not nice to look at, but we don't have to actually generate the table. It's there when you it's there as static data, and you don't have to have the code to generate the data because you have already generated it. But obviously this is insanely inflexible because now you definitely can't. If you want to change the polynomial, for instance, you have to do a manual work. So it's good in these regards. It kind of sucks in that regard. So the sort of final implementation for this, we want to use a pre-computation table, and we want to have it static, but we also want to have it flexible. So we want all three. So we go into this. So this is basically the same again. So all this stuff is the same as before, so don't mind that. But here we have this instead. So we have a static const pre-computation table, which this will be just a std array. And there is some magic going around here, but basically we will instantiate an std array from 0 to 255, and for each value in that array we will initialize it by calling this static function here. So this is pretty straightforward. There's nothing complicated about that, except this make compile time array, which is a little bit magic. So part of it is stolen from Stack Overflow, so just attribute that. But this is basically it. So there is we have a template function. You give in the type name. It was uint32 in this case. And you have n, which is the size of the array you want, and here you have a function which maps from an integer, which will be 0 to 255, and back to uint32 that we specified there. And then it goes through this stuff, and it will magically generate a table. And just to show how this works, this is just to show that these are the same types. And here you call this sort of magic gen sequence, which is this one. And let's do it with some color coding. So you have these three. You basically have these three versions. You have sorry. You will have you have two gen sequence and one sequence. So if we look at this color coded, so if you are here and we say we want let's limit our size now, so we want a table that's three entries long, so 3 times uint32. So with this we say n is equal to 3 there. So then gensec this, and if you look here, it inherits from this one. So here you subtract 1 from n, and you pop or you push n minus n to that list as well. This one in turn, it again inherits from this one. You subtract 1 again, and you push the new value there. And if you do that iteratively, in the end, you're going to go to this specialization, which has n equals 0. And it in turn inherits from sequence, which is 0 up to n minus 1, which is what we wanted. So you have this. So basically, this call here, again, we have a specialization, so we can sort of unpack this. So we have a sequence, and we can, by using specialization, we can unpack this and pop out the is ... which is the R0, 1, 2, 3, 4, and so on to 255. And here we just apply the function to each of those values. And so then our implementation can just be this, which is the same as, or more or less equivalent to just this, except we don't have to do this sort of manually. We just have it automatically done for us by this. So it has the same features as the previous one, basically. So you don't have to generate the table in runtime. So you don't have to take the time to generate the table, and you don't have to have the code to generate the table. And it's relatively flexible. So if you, this isn't strictly needed for this, but necessarily, but I added the polynomial as a template argument, so you can just specify any polynomial you want. As this is a static const, if you have 50 different instances using the same polynomial, you're still going to have just the one table. And if you have 50 using one polynomial and one instance using another table, then you're going to have 2 different tables. So it's relatively. So this is just done once at compile time for each of the polynomials you specify. And also, as I said before, this isn't the idea with this isn't that you're necessarily supposed to take this particular code and it's more as again with the fashion show. This is more like general inspiration for stuff to do in compile time. And this particular thing, I mean, it's not limited to CRC32 by any means. You can use it for any lookup table. If you have, I don't know how valid this is in the gaming world anymore, but like in a long time ago, in the DOS times and those, when you had all these trigonometric functions, sine and cosine and whatever, you used to sort of pre-compute them into tables because the actual math functions were too heavy, basically, to do in runtime. So you can use it, but you can use this for any kind of pre-computation table, basically. Should we? Can someone run? Oh, sorry. Yep, sure. Yep. 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 Depends on what you're looking up, I guess. I mean, of course, it's going to be a trade-off. I think in general, the cost of looking up a value in a table is quite small. So of course, if the function, if you have a very small function call, of course that might be, I mean, in some cases faster, but in this particular case, for instance, and if you have a like sine or cosine or whatever, it's definitely going to be faster to look up in a table than, unless the table is huge. But yeah. Yeah. I think as with everything else, I mean, if you want the best performance, you just have to measure and see what works out basically. Yeah, but regardless, it's a kind of a it's a general strategy. That's the point. That you can make these lookup tables in compile time. So next thing, this isn't before I go into the actual things. It's a disclaimer that this is I think the idea behind this is quite valid. The code I'm showing here is something that I sort of just threw together a while back, and I haven't really had time to freshen it up. So think more about the ideas than the actual code. That's the disclaimer. Okay. So you have so depending on what you're doing, I mean, in some use areas you end up dealing a lot with like buffers, which you have like basically just treat as a byte arrays when you have to index and slice and write and read and do all this sort of back and forth. I mean, it could, for instance, be a pixel buffer if you did things with sprites or whatever, or if you had this CRC32 example, for instance, that was for a serial communication protocol, and there, of course, we have all these buffers, and since you're saving space, you have them in you have all these pointers in unions, and you have to a lot of pointer trickery basically. And the stuff you do with raw pointers, you typically memset them or memcopy or memcompare, and what it's not so great about that is that it's easy to make small mistakes, and you have to do a lot of bound checking, and so you're not off by one and so on. And typically you do most of the bound checking in runtime. But you can do quite a lot of it in compile time as well. And that's what this is about. So of course, like with any error, you want to catch them as quickly as possible. And the best sort of type of error you can have is a compile time error, because that's something you catch very quickly. And if you can put a bound check in compile time, then you don't have to do it in runtime, basically. I mean, if you already checked something and you know that it's correct in compile time, you don't have to check the same thing in runtime, basically. So that's, again, you can get safer code because you are checking your bounds and you're catching the errors earlier, faster, because you can skip some checks in runtime, and for the same reason also it's more code. So this is just to go through the particular implementation I did, but which it's not perfect, and you could do it other ways, but this is just to illustrate the point, basically. First, you have a buffer class, which is really just a pointer to some memory and a size. So just a pointer and std size t. Then you have a separate version of it, which is a fixed buffer, which is the same thing, but where you say that, okay, I know the size of this buffer in compile time. So this is a template where you have the size of the buffer. And since you have the size, since the size is known in compile time, you don't have to have it in runtime. So you have, instead of a pointer and a size t, you just have a pointer. So that's really just a single pointer. Of course, you have a const version of the buffer and a const version of the fixed size buffer as well. So it's a little bit diagram. So here we know the size in compile time, and here we know the size in runtime. So this is just a pointer, and on this side you have a pointer plus a size. And these two, they don't, or these four, they don't own any data. They are just wrappers to something else that, or references to something else that owns the data. So we have another class, which is a static buffer, which is a fixed buffer as well, and that owns a particular chunk of data. And we have a dynamic buffer, which is here, and it owns a particular chunk of data. So this is basically as a wrapper for a array, and this is basically as a wrapper for a unique pointer, where we just create the memory with make unique. So it looks something like this. So you have a single const pointer, a single non-const pointer. You have a const pointer and a size, and this is basically just the same. So pointers plus size. And these don't own any data. And these two, they own the data, and here you have just an array and just a unique pointer. So yeah, static buffer, put it on the stack or a static data or wherever, and dynamic buffer, that's does memory allocations. And it's a wrap, since it's a wrap for a unique pointer, just if you want to move the data to some other dynamic buffer, you just use the normal std move semantics. And so let's skip that. So fixed buffer, it's a single pointer, and buffer is a pointer plus a size. Since these are kind of small, you're supposed to pass them by value, not by reference. So you're supposed to use them like this and not like this. So this is the big one on a 64-bit architecture. This is 16 bytes, and this is just 8 bytes each. So it's cheaper to pass them by value than by reference. All right, so you have a bunch of methods. You have take and skip. This is just, can argue with whether naming is all that great, but basically just slicing the array, slicing the buffer. So skip is just take some portion of it, and take is the same, but you specify a starting index and a size as well. So that's just basically slicing. Sets, we have two methods to fill the buffers with something, which is basically just wrapper for memset. And you have another which is for copying, which is copying and equals. So you have wrapper for memset, memcopy, and memcompare, and just for printing as well. And so all these have a ton of different overloads. So if you have take here, for instance, you have two size parameters. You have the index and the size. So you sometimes you know the index in compile time, and sometimes you know the size in compile time, and vice versa. So you have basically 4 different versions of those, where you have either by template or by sort of as a function argument, basically. So if you have something like this is just a very trivial thing here. So just create a static buffer, because you need either static buffer or a dynamic buffer, or we could easily wrap some other buffer with the sort of wrapper classes, but these are kind of convenient for when you have some ownership of the data. So let's create a 20-byte big buffer on the stack, just fill it with some crap, and just call this function, and this just works as you would expect, basically. So this is just a uint8 pointer to the data. But if you do something like this instead, we have a static buffer which is less than that, then you will get a compile time error, because you have in the constructor you have a static assert, so that runs in compile time. So if you do have this where you slice things, then you will get instead of in runtime, you will get this in compile time. Of course, if you have a dynamic buffer, the point of all the sort of buffer classes on the right side is that the sizes aren't known in compile time; they're only known in runtime. So then instead, if you do the equivalent of that, you will get you get the error in runtime instead. So basically, if you stick to the semantics, then if you have an error which can be caught in compile time, you will catch it in compile time, and if an error which can't, then you will sort of catch it in runtime instead. So yeah, you have all these methods. So you have basically this. So here you just take a slice of A, and you take another slice of B, and you just copy the data. And yeah, so these two versions are basically the same thing. So yeah, as I said, if both buffer types are fixed, then the error checking is done in compile time, and otherwise it's in runtime. And if you have something like this, we have two fixed buffers, and you copy some particular chunk of them. You copy the first 50 bytes of source to the first 50 bytes of destination. Then this is a resulting assembly of it. So I mean, this is basically just memset with some weird optimized version of it. So in general, if you do all this template stuff, if you run without any optimizations, you will get a ton of function calls all over the place. But as soon as you enable optimizations, you will basically just condense down to single instructions for most of the stuff. So this is okay. You have all this template class, but it's if you enable optimization, it's just a pointer. So yeah, so these are not perfectly implemented by any means, but the main point is to show that okay, it's probably a good idea that if you can make your code so that if you play around with buffers, that if you can catch bounce errors in compile time, that's probably a better idea than having to catch them in runtime. So that's the main idea behind this. So, all right, we have half an hour. Where is it gone? A half an hour. I have a third example, which is isn't really meant as a serious thing, but it's kind of like I had these two things that I thought about this for this particular talk, and I thought that might not be enough, so I dreamt up a third thing, which isn't really serious, but it kind of ended up being quite big. So I will, since we're like 15 minutes left, I will kind of rush through a lot of details, basically. But so this is weird stuff. So you want to a little bit inspired by Olaf's talk about where you have this this messaging system. So yeah, this is okay. So you often run actually, I mean, having some kind of data in JSON that you want to be use from your code is quite a common use case, actually. You have message specifications between different platforms, and you have different hardware configurations and register settings and whatever. And JSON is a very simple format, so it's which is why it won the war against XML, I guess. So if you do want to generate code from a separate script, you have to integrate it in the build system somehow, typically, which can be a little bit messy. And then, of course, when you build it, you have to have on the platform where you build it, you need to have Python installed or whatever you're using to generate the code. It's actually not a big problem because it's usually pretty convenient. So as I said, this isn't serious stuff. It's more. But this is a maybe more important point. It's something that should be possible, basically, to do in pure C++. So it would be really nice if it were possible to do it in pure C++. It's from some kind of purity perspective, it's nice to do it in one language instead of having to take outside help, basically. Okay, so JSON is basically as this. You have numbers and strings and booleans, and you have lists and dictionaries, and you have the value null, and that's basically it. So it's a very simple format, which is its main strength, I guess. And this is trivial to parse in runtime, but now we want to parse it in compile time. So instead of let's just dive in. So if you have a template, usually you have the parameters for the template, so usually types, but you can have values as well, but you can't have just any value. You can't have strings, for instance. So yeah, there we are. So it's fine to send in an int as an argument to a template. Sorry. Yeah, but this is it's not. We're off to not serious stuff anymore. So yeah, it's comic sans. Okay, but you're not allowed to do this. You're not allowed to send in strings as template arguments. Which, if you want to parse stuff in compile time, this is kind of sucks. So if you take some stuff and put them together, you can have something which sort of makes you have strings in as template arguments. So let's see here. Where should we begin with this? So let's start with the user-defined literals, which is new since C++ something 11, I guess. Yeah. All right. So typically you will return some particular type from a user-defined literal operator, but apparently this particular setup is perfectly fine according to the standard. So you have a so you're sending in as a sort of template argument type name C, which is the character type, regular char in this case, or a v-char-t if you're using a wide string, and then just the individual characters as values. So you can do this where you instantiate this class here. Yep. And we're not actually interested in the actual object here. So that's why we need, or we don't need, but we want just the type of this object. So that's why I have this macro here. So if we do this, then we get basically the equivalent type. We get this J string, you get a string where you have this C is char, and the first value is P, and the next value is R, and so on. And that's a type, so that's perfectly fine to use as argument to template. And it's pretty easy to print this stuff, since we declare a static const expression C string, so we can just print that if you want to as well. And again, with all this const express stuff, basically if you're not using it in runtime, it's going to just disappear. So this string only exists if you actually use it in runtime. But as I said, we have to run through some details. Just create a little bit nicer print function with some tag dispatch. So instead of doing this, we can print our string like this. And the point about this is that it's very easy to extend to a lot of other, because we will end up with like a billion different types. So this thing is very easy to just be able to create print functions for all kinds of types. All right. One problem is how do you get the JSON data into C++? It would be nice to be able to just read it as a file, but we can't because I/O functions aren't context. All right. Okay. Okay, that's good. Nice. Shit, my beer overflowed. Thank you. I got so. In any case, it sort of almost works out with include, but it doesn't because of this stupid preprocessor rules. But you can get something that's almost okay using raw literals. So you can have it in your C code. You can have it like this. So you just copy paste your JSON in there. It's not perfect. You can slightly better version. If you just wrap your JSON data with this R with raw literal begin and raw literal end, basically. So you have this sort of preamble and this post, whatever it's called, and then you can just include it. Yeah, so it sucks that you have to wrap it in that, but you can have it in a separate file instead of just as JSON data. All right, so have a list function, which is this, or sorry, not list meta class, I guess. So it works basically, it's just a wrapper for std tuple, basically. But we have defined some methods for it. So if you have a list, you can concatenate two lists. If you have a list, you can append a value to a list, and you have this all function, which checks if you feed it a list and some predicate, and it returns whether all values or all types in the list satisfies that predicate. You have a map function, a reduce, flatten, and filter. So you have the sort of standard list functions you have in most languages that supports list comprehension to some degree. So if you have something like this, if you concatenate two lists, then you get, so you have ABC and this is ABC and DE. So if you concatenate two lists, then you get one big list. If you append a value, you get this. You map this sort of add exclamation point, and you get this. Reduce, so you smush together all the values in the list, a single value, actual types in this case, but and flatten is just a nice sort of small utility to if you have list of lists, so just flatten them together. We're running out of time, but same stuff for string, and you have the normal string functions like substring and equals and starts with and so on. Like comparing two strings, if they're the same, it's very, very trivial because you just check if are they the same type or not. And concatenation is also pretty trivial. You just unpack the individual characters and you just return a new type. So that's fairly straightforward. Substring, it's a bit messier. You have to resort to this sort of gen sequence stuff from CRC32 example in the beginning. But it's doable. So you have a substring function, so you can, if you have a string, you can say I want this particular chunk of the string. All right, so we start building stuff from this. And we want to parse out, same as before, we want to parse out numbers, strings, booleans, lists, dictionaries, and null. And we skip floats because it's, I didn't have time. So we have, what the stuff, this is what do we want our result to be, basically. So if you have an integer, we want this as sort of output from our parser, which is just a simple class which has a const expression value with the actual integer. Oops. More or less the same with the string. This is just a wrapper for the string class or the string sort of meta class we defined earlier. So the strings are a bit different because you actually this particular case we're treating it as types and not as values. But if you want, you can have the C string. And boolean is same as integers more or less. And the list is also a thin wrapper for the sort of the general list class. And dictionaries we define as lists of key value pairs. So lookups for big dictionaries isn't very fast, but simpler than a, I don't know, tree. So if we have some JSON data that looks like this, what we would like out of this is this instead. So we just want a list of two integers, a dictionary, and the boolean value true. So that's basically okay. We have this in, and we want this out. So we create a parser. First parser is just a literal, where you throw in, I want to parse an actual plus sign or a minus sign or a comma sign or typically signs of some kind. Just to run through the stuff. Now let's skip Comic Sans. All right, this is a literal parser. Yeah, I'm not going to go into how the results from the parsing is done. Next one, you just feed it function. So this is basically the same as if you have a regular expression. This is basically the same as plus. So if you have a white space, for instance, \s plus, for instance, this will do that. So you have to find a bunch of this, the normal C-type functions on the const expressor. So let's find our own, and then you can do things like digits is or white space, which is one or more white space or one or more digits. So that's the same as the regular expressions. And let's define an AND operator, so you can combine two parsers. So basically, it will match if the first parser matches and then the second one, or which is either or matches. Obviously optional, basically 0 or 1 and 1, 0 or more. So then you can combine these literal and the digits and white space and all those. So you can combine them into more complex things. So if you do combine them into more complex things, here we have an expression for extracting an integer, which is basically starting with a plus or a minus optionally, and then just a bunch of digits. So we're skipping floats here. And Boolean is very simple. It's either the literal word true or the literal word false. And then you say, okay, we'll call it a primitive, which can be either Boolean, an integer, or a string. Space is just white space. Yeah, we have all this built up. One interesting thing to note here is that all these sort of types refer to other types, which sort of gets us into trouble if you have a list which can contain other lists. So we have this hack to get around that. So if you have, for instance, where do we have it? We have a list. It's basically this list values, which is here, and from here we have value. A value contains a list, so then we have this recursion. So then we have to use this hack to get around that, basically. So then we get rid of the recursive type referral, basically. And so if you make a small test program from this, so you just have, this is all it is. So you just include the, did I have the messages, Jason? Oh, it's the same as before. It's just, where is it? It's this. So it's the same as before. So just include the JSON data. You just parse out the result. This could be maybe put in a nice wrapper, and you just print out the result. So there we have it, basically. It's this is quite noteworthy. It takes 2 seconds to compile this on a pretty decent computer. No. And if you add more data to it, it grows kind of quickly. So the point with this wasn't to do something serious. It's more like, okay, it is sort of, at least in a sort of theoretical sense, possible to do this. And we're way out over time. But so when I was kind of finished with this and a bit tired with it, I came up with quite a better way of doing it. So it could be done quite a bit faster and could be quite a bit nicer. The main thing why is there all this template crap, because you can have all this const expression function which takes in const expression strings. So but the problem we run into that is that when you're using values at compile time, you can't allocate stuff dynamically, and basically we're building up. You have a string, and from that you build up a tree dynamically. And that's fine doing it with types, but you can't actually do that with values in the same way in compile time. So that's why I ended up with all this template stuff. But JSON is such a simple format, and what you would typically want to use this for is to generate some types for, I don't know, a message class or whatever. So a more sane approach to this would be just have a simple iterator and just sort of run, because JSON it's trivial to iterate. I mean, if you just look at one sign, you know what kind of token it is, and most tokens are just a single character, and for the ones that aren't, it's trivial to find out how long the tokens are. So it's tokenizing JSON is very simple, and it's a very simple format. So you could just get by with an iterator basically. So that's So in summary, it's kind of doable to parse JSON at compile time, but okay, it's slow as hell. I'd like to emphasize that this is a toy thing, that there's more, again, inspiration that it is possible to do complex stuff in compile time, not that you should necessarily run off and do it. Yeah, you can do a lot of things in compile time which might, at first glance seem difficult. And it is difficult. I mean, it's this parsing this stuff in runtime is trivial, and then it took quite a while to put all this template crap together. So it's not. So it is significantly more difficult to do, especially if you have to do it with templates. It's significantly more difficult to do it in compile time than in runtime. That's basically it. And I have all the code on GitLab. So if you are interested in looking at it's a very uncensored version. I haven't had time to clean up stuff, so it's and again, it's just for inspiration, not yeah. So that's it.